everyone. My name is Ranjit Gupta, and today I will be presenting my computer vision project for the MTech Geoinformatics program at Indian Institute of Space Science and Technology, Thiruvananthapuram. This project is titled Automated Building Footprint Extraction using GeoAI and Mask RCNN. What exactly is building footprint extraction? It's the process of identifying and delineating the 2D boundaries of buildings, typically from high resolution satellite or aerial imagery. This data is essential for a wide range of applications, including urban planning, disaster management, and various smart city initiatives. Our project focuses on leveraging geospatial artificial intelligence, specifically a model called Mask RCNN, to automate this extraction process. We have utilized the GeoAI library within the Google Colab environment with the aim of developing a solution that is scalable, accurate, and generalizable. The primary challenge we are addressing is driven by rapid urbanization, which demands efficient and up-to-date mapping. Traditional manual digitization, while accurate, is incredibly time-consuming, expensive, inconsistent, and doesn't scale well for large areas. Moreover, conventional automated methods often struggle with the inherent complexities of urban environments, such as variations in building shapes and size, shadows, and image quality. Therefore, our problem statement is to develop an automated GeoAI pipeline using Mask RCNN. Specifically, this project aims to achieve automation to eliminate the laborious manual annotation by using deep learning for detection and segmentation. And second, accuracy to achieve high precision in identifying building boundaries, even for complex shapes and in dense urban settings. And third, scalability to efficiently process large geographical areas using tiled imagery processing and cloud computing resources. Both generalizability and critically to validate the model's performance on imagery from different sensors and geographic regions, in our case, comparing results from data acquired in the USA versus India. Let's move on to the data for training our model. We use NAP imagery, that's the National Agricultural Imagery Program from the USA. The specific imagery is from 2023, centered around 5 Mile Prairie in Spokane, Washington. This is high resolution aerial imagery, approximately 60 centimeter spatial resolution, and was initially multispectral, which was containing RGB plus NIR bands. The bounding box for our training area is shown on the slide. For our ground truth levels, we utilize the building footprints from the Overture Maps Foundations accessed by the Microsoft Bing Open Dataset. For our specific training extent, this provided 412 unique building instances to ensure accessibility and reproducibility. All training and test data were hosted on Hugging Face under the repository of our this provided ID to ensure accessibility remotely. For testing the model's generalizability, we use the different datasets from Kochi, Kerala. This data was sourced from Open Aerial Map. The imagery was captured by the WorldView 2 satellite provided by the Digital Globe Open Data Program. It's also high resolution at 50 centimeter and was acquired on February 1st, 2018 as a 3-channel RGB image. Our specific test area was a clipped region near the Jawaharlal Nehru Stadium in Kochi. Raw remote sensing data isn't directly suitable for deep learning models. A key challenge is that models require fixed size inputs, while our satellite imagery is often very large. Also, our 4-channel NAB training data was incompatible with standard 3-channel pre-trained models. So, our pre-processing workflow involved several steps. First, image tiling. The large NAP training image with the dimensions 2458 by 1460 pixels was divided into smaller 512 by 512 pixel patches. We used a 256 pixel overlap between tiles. This creates manageable inputs and importantly ensures that buildings aren't cut off at the edges of tiles, which helps the model learn complete shapes. This process yielded yielded 45 tiles for our training area, as you can see from the tile overview. All generated 45 tiles containing building features. Like here also, after doing the image styling, here we just visualize the how 45 image stylings are separated in 5 by 9, and also this figure resembles that green contains features and red if there are the red dots where there is no feature was detected, but in that in everywhere tile contains the features, and here we get each tile has a label, no empty label present. Continuing with pre-processing, channel conversion. The initial 4-channel NAP imagery, RGB and NIR, was converted to 3-channel RGB imagery by dropping the NIR band. This was crucial to match the input requirements of the mask or CNN model, which is typically pre-trained on RGB datasets like COCO. And fourth, next the vector next one our mask generation, that was the next the vector building footprints, our ground truth, were converted into corresponding binary raster mask for each image tile. Pixels inside the building were given a value of 1 and background pixels were 0. This mask provide the pixel level ground truth that the model learns to predict during training. An analysis of this mask, as shown in the chart, indicates an average feature distribution where about 7.81% of pixels belong to the building class across the training tiles. Now, let's talk about the heart of our project, the mask RCNN model. Mask RCNN is a deep learning architecture designed for instant segmentation. This means it is not. This means it not only detects objects but also provides a precise pixel level masks for each instance. It's an extension of the faster RCNN framework. For each individual building instance, mask RCNN simultaneously predicts its bounding box, a class label like building or background, and a precise mask outlining its exact shape. Why did we choose mask RCNN for building footprints? It excels at delineating irregular shapes and is particularly good at separating adjacent buildings, which is a common challenge in urban areas. Studies have also shown it can outperform other models like YOLO in segmentation accuracy for complex scenes. Uh, the mask RCNN architecture has several key components. We use the ResNet 50 network as the backbone, augmented with the feature pyramid network FPN. This combination extracts hierarchical features from the input image at multiple scales, which is a vital for detecting buildings for varying sizes. The RPN efficiently scans the feature maps from the backbone and generates candidate bounding boxes or regions of interest that are likely to contain buildings. ROI align this layer takes these proposed regions and accurately pulls features from each one. It uses bilinear interpolation to avoid misalignment issues found in older methods like ROI pool, which is crucial for generating precise masks. Uh, Finally, for each ROI, there are parallel branches that perform the classification, refine the bounding box, and generate the high resolution pixel-wise mask. An important aspect of our approach was transfer learning. We utilized the mask RCNN model pre-trained on the large COCO datasets and then fine-tuned it using our specific building footprint data. This speeds up training, improves the model's ability to generalize, and means we need less domain-specific training data. The model training was conducted using GeoAI library within the Google Colab environment. First input, our training set consider of the 45 pre-processed 512 by 512 RGB NAP image tiles and their corresponding binary masks. Process, we fine-tune the pre-trained mask RCNN model Hyperparameters, we trained for 100 epochs with a batch size of 4 and a learning rate 0.005 and a 20% validation split. Performance, the model achieved a best validation intersection over union of 78.6 percentage. The graph here shows the training loss decreasing and the validation intersection over union increasing, and then stabilizing, indicating the model was learning effectively. You can also see some sample predictions on the training uh, not training validation data. We can see some sample predictions on the validation data, how it was predicted by using our model. This was the ground truth, and this was the our validation data on prediction. Let's see some minor changes in that our prediction we get, like some minor changes in the shape as we can see here. Loss function mask RCNN uses a combined loss function that considers classification error, bounding box regression error, and mask prediction error. Challenge, a significant challenge was the GPU limitations in Google Colab. This sometimes necessitated training on a CPU or using a reduced batch size and a number of epochs, which means the model might not be as fully trained as it could be with more robust resources. Once trained, the next step was inference on our unseen test data from Kochi. The main goal here was to evaluate the model's ability to generalize its learning from spoken net data to a different geographic region and a different sensor. Our inference pipeline involved a sliding window approach. Uh, the trained model was applied to a 512 by 512 overlapping tiles with a 256 pixel overlap across the large Kochi test image. This allows a fixed size input model to process a large image. For each tile, the model generated predictions, bounding boxes, class labels, confidence scores, and segmentation masks. Non-maximum suppression was then applied with an IUV threshold of zero point 0.5. This is to merge overlapping detections that often occur due to the sliding window and retain the most confident one, effectively removing duplicates. Finally, confidence filtering was used in detections with a confidence score below zero point 0.3 were discarded to remove low certainty, likely false positive predictions. The initial output of the stage is a raw raster probability map, as you can see on this slide, indicating the model's confidence that each pixel belongs to a building. The raw raster outputs from inference need further refinement. This is where post-processing and vectorization come in. We use the building footprint extractor class from the GeoAI library for vectorization. This process identifies contiguous high probability pixels from the raster map, converts these areas into vector polygons, applies NMS again if needed, filter these polygons based on criteria like a minimum area. We used 10 square meter and simplifies their geometry. Results, initially 992 objects were detected. After this filtering within the vectorization step, we extracted 966 building polygons for our Kochi test area. The image shows these extracted polygons overlaid on the Kochi imagery, colored by their confidence score. And here you can see the statistics for these confidence scores, a mean confidence of about 78 percentage, which is a quite good. Now, next we explored regularization to improve the geometric quality of the extracted raw polygons, aiming to make them smoother, enforce orthogonality where appropriate, and generally make the footprints look more realistic or map-like. We applied several methods using GeoAI functions. First, standard regularization. This focuses on ensuring rectangular and orthogonal shapes using parameters like minimum area, angle threshold, orthogonality, and rectangularity. Hybrid regularization. This combines multiple techniques for a more balanced result. Adaptive regularization. This adjusts parameters based on the building size and shape. Note, in this particular run, The regularization methods with the chosen thresholds resulted in minimal changes to the polygon shapes. This might suggest the initial vectorization was already quite good or the thresholds were conservative. Like here, the here we see the our regularized in that so many uh, uh, here that shape was not in this realistic looking like a realistic, so that's why we apply some regularization parameters, but in that regularized we get the changes, sudden changes occurs in the shape, and after applying the hybrid regularization parameter it was look like a fully like a rectangle. If the buildings are in circle then also it looks like a rectangle. And adaptive regularization it was the based on the building actual building size and shapes. If the building shape is the circle, from the top view it looks like a top circle. The final step in our post-processing pipeline was further filtering and analysis based on geometric attributes. We calculated attributes like area, perimeter, elongation, and compactness for each extracted polygon. This allows for quantitative analysis and rule-based filtering. For example, we could filter out polygons that are extremely large, example area greater than 1000 meter square, or have a very high elongation factor, example greater than 5, as this might represent errors for large non-building structures. This helps eliminate potential errors or misclassified non-building objects. The image here shows the footprints after such potential filtering, visualized perhaps by area, and this was the graph in our this test area, how much square meter of building number of building areas are presented. It was the histogram of that area. uh, Now in conclusion, this project successfully demonstrated an automated pipeline for building footprint extraction. We achieved a validation intersection over union 70.6, and importantly, the model showed good generalization capability when applied to the diverse Kochi test data, successfully extracting 966 building polygons. This pipeline offers a scalable and potentially more efficient alternative to manual methods for urban mapping applications. Now, limitations. However, the study has its limitations. Computational constraints in collab impacted optimal training. The training data volume was relatively limited. We lacked ground truth for the Kochi test set for a full quantitative evaluation. The model still faces challenges with very small, irregular, or densely packed buildings and occlusions. The chosen regularization parameters had minimal impact. For future work, we propose several directions: utilized enhanced computational resources for retraining, expanding and diversifying the training datasets, experimenting with different model backbones or boundary refinement techniques, optimizing post-processing parameters, and another crucially obtaining the ground truth data for the test areas like Kochi to enable robust quantitative evaluation like calculating precision, recall, and test IOU, exploring integration with other data sources like LiDAR or SAR, potentially extending this to 3D building modeling, and finally developing a web applications for real-time mapping capabilities. These are some of the key references that inform this project, including foundational work on mass RCNN and faster RCNN, as well as studies on applying deep learning for building footprint extraction. Thank you for your attention. I am now happy to answer any questions you may have.